Okay, so what I want to do now is I want to shift gears and I want to go to the binomial coefficients. How many of you have seen binomial coefficients before, the n choose k's? Okay. How many of you have seen Sierpinski's triangle? Okay, so I'm going to ask you to stay quiet for just a little bit. Okay, so what I want to do is I want to explore. And so we can explore one of two ways. We can either do it on the board, or I can show you a little movie of it that I made. Up to you. On the board? Alright, we'll do the board, then we'll do the movie later. Okay. So Pascal's triangle. So it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5. Oh, now you see why I wanted to do the movie. 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1. And I'm going to say I've run out of room after the next one. 1, 8, 28, 56, 70, 56, 28, 8, 1. How many people have not seen Pascal's triangle before? Okay, excellent. So the rule we have is each number is formed by adding the 2 above. And there's a nice interpretation for why we care about Pascal's triangle. So if we look over here, this is what you get when you expand x plus y squared. This is what you get when you expand x plus y to the first. This is what you get when you expand x plus y plus cubed. So it's x squared plus 2xy plus y squared. X cubed plus 3x squared y plus 3xy squared plus y cubed. And so the real question is, why does this rule give me the coefficients of this expansion? So how many of you have taught that to your students? How many of you have had your students use that without being told why? So there's lots of different ways you can do this. And so I'll give you a quick proof as to why this is true. And then depending on how much you want to talk about combinatorics, I can tell you some ways of proving these things. How many of you have students where you've used binomial coefficients, these n choose k's? Okay. How many of you, okay, so I'll try to give you a few of them because it illustrates some really nice points. So let's look at x plus y cubed. So I think I know how to do 3 things in mathematics. And right now we're going to be doing the same thing we've already done the first 2 times again. I'm going to write x plus y cubed as x plus y squared times x plus y. And then the question is always, how much detail to go through a calculation like this. I want to go through enough detail so you can get a sense of what's going on. Let's choose a coefficient of x plus y cubed. Maybe we're interested in the 3x squared y term. Well, how can I get an x squared y term? Well, I'm multiplying these over here. So to get that kind of term, I could have a term from here hitting x. So what term would I need from here to hit x to get x squared y? I would need the xy term. And from the other one, if I'm hitting y, what term would I need? The x squared term. Well, the xy term from this side is the 2xy. And the x squared term is just the 1x squared. So the way I get an x squared y term is I have to add these together. And so I get 3x squared y. And if you think about what's happening, well, the 2xy term was this, the x squared term was this, and that's where this number 3 comes from. there's nothing special about taking cubes and looking at the x squared y term. I could take the nth x plus y to the n. And I want maybe the kth term. And this is where I'm getting this relationship from. This is where Pascal's triangle is coming from. It's how I group things. The only way I can get a x squared y term is I have to have a xy term here hitting x, or an x squared term hitting y. And again, there's a couple of things here that are being subtly assumed. When I multiply this out, I'm never going to get an x to the fourth. Well, that makes sense. Each term I have either an x or a y. So my terms are going to go from no x's to 1x to 2x's all the way up to 3x's. And in each term I either have an x or a y, so the sum of the exponents of x and y has to add up to 3. So the only possibilities are x cubed, x squared y, xy squared, and y cubed. And this gives you an idea of where Pascal's triangle comes from. So it turns out that there's other ways of looking at this. So instead of looking at it by multiplying like this, I can look at it in terms of combinatorics. And so the combinatorial approach is the coefficient of x to the k, y to the n minus k in x plus y to the n is just n choose k. Sometimes people write this as nck. This is n factorial over k factorial n minus k factorial. Out of curiosity, how many people have seen this? How many people have not seen this? Okay. And so I'll think about how much more I want to say about the combinatorics here. Alright, so what I want to do is I want to do something new to Pascal's triangle that hopefully you and your students haven't seen that might excite them about seeing something like this. What I'm going to do is I will go through my triangle, and every time I have an odd number, I will make it a black circle, and every time I have an even number, I'll just erase it. And let's see what we get. Alright? I guess maybe because I've already written things in red, let's make it a red dot. 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 I went to Yale, I don't mind using up Harvard's markers. I think we would erase that. In this row, everything is odd. In this row, we would erase this, we would erase this, we would erase this. Now if you think about it, the way we get an element is we add the two ones above it. We always have ones going along the edges. Even plus even is even. Even plus odd, odd plus even, odd. And then odd plus odd is even. So if you heard the phrase modulo, I'm doing modular arithmetic, I'm doing clock arithmetic, I only care about what happens up to multiples of 2. And so if you think of this relationship, so here, 5 and 10, one is odd, one is even. When I add them, I will get an odd number. It doesn't matter right now, I can replace this 5 with just a dot to indicate that it's an odd number. I can replace this with an empty thing to indicate that it's an even number. I don't care that this was 5, I don't care that this was 10. I just care odd number, even number. And so their sum will be an odd number. So this would be erased, this would be kept, this would be kept. Okay. This would be erased, this would be erased, this would be kept, this would be erased, this would be kept. We have 2 more rows to do, we're almost done. Oh, this looks like a great row. What's happening in this row? I'm sorry? They're all odds. Well, if they're all odds, what's going to happen in the next row? All evens except for the extreme ends. So, again, think back to the hourglass, the sands are running. Every moment you do in class is a moment you don't have for other things, and there are certain things that are going to be tested for your students. What pattern do you see here? Do you see any patterns? Would it be easy if I added certain things back to try to see what the patterns are? sorry?
Are they isosceles triangles?
Ah, so it looks like there's missing some triangles. And again, this is where it's sad that I'm not, as good of a writer. It looks like there could be a triangle hidden in here. Because we had that one dot that was destroyed. So maybe there's some kind of triangle from that dot. And over here, there was a dot, there was a dot. And now if we think about what here we have boom, 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 boom. So it almost looks like, here is an equilateral triangle. Maybe there's one here, and one here. And now we just had all these dots that were destroyed. So this is not an accident that I stopped at this row. What's going to happen is I keep going. These are even plus even is even, right? So this is going to stay even for quite a long time and give us a giant even triangle coming down. Now, the odds from over here, the odd interacting with the even, is going to give us an odd. And so, in terms of what's going to happen on this side, it's going to be a little bit more complicated. But now, whenever this interacts with something over here, what is that going to be? It's going to be odd. So these are all evens here. So as this one interacts with here, it's going to give me all odds going down. Well, my Pascal's triangle has all odds coming down here. Does this look familiar? Yes! This is the top! Right? I was hoping somebody would go, ah! Right? It's the top. How do we define the top? We define Pascal's triangle by taking two diagonal lines of all odds and then defining the interior by taking the two things that were above and just adding them and just saying even plus even, odd plus odd is even, odd plus even, even plus odd is odd. That's the exact same game. So this pattern over here would now come in here. This pattern would also come in here. And this is a great introduction to fractal geometry and chaos theory. So what I thought I would do is I'll show a little movie now. So I was lazy when I wrote the computer program. Instead of doing an equilateral triangle, I'm doing a right triangle. And instead of having the axes scaled equally, the axes are scaled a little bit unequally. So just to warn you, when you're viewing the video, it's going to be drawing the triangles like this. It's going to be drawing at an angle like this. So it's not going to be quite as nice as this. Eventually I will clean up the video. But I've done stuff like this with my kids. And so, my kids have enjoyed seeing the pictures and seeing things emerge. Okay, so now...
So you would teach Pascal's triangle in geometry?
So you can teach it in many different ways.
I've only taught it before, like pre-cal, or maybe algebra 2 probability.
Right. And so one thing is, if people have seen it before, this is another way of looking at it, of revisiting it, or this is a way to try to motivate some geometry.
So how much of this, it's cool to see once, but
right.
How much of it do they actually need to take from there? Because I find that they often only expand, or at least after they learn it, they only really expand, a quadratic or a cubic.
Right. So to me, it's more this idea of playing with math, of just exploring and seeing where things go.
A colleague and I, many years ago, developed 3 PALs, problem of the week, one for all based on Pascal's triangle, one for 6th grade, one for 7th grade, one for 8th grade. and each year they discovered different patterns in it. Like the powers of 11 are in
Yep.
there, and I don't remember what the 6th grade one was. The binomial expansion was extra credit for the advanced kids in 8th grade. There's just so much in there. You could do it at all levels, just about, and have something.
I think building on that, what's more important is the journey, not the destination. That it's not, I'm trying to get you a certain fact for you to spit out on an exam. I want you to look at math, I want you to play. I want you to try to find patterns, I want you to try to find questions to ask. So I believe most researchers train monkey work. Is you have a bunch of us who are trained similarly, we can solve the same problems using the same tools. The difference is who asks which questions. And so let me just play the short movie. This was done in Mathematica. Try to stay low enough a second. So this should go. So it's adding the dots one at a time. And so it's putting in the different rows. And so you can start to see the pattern emerge. And so what I like about this is, this is a very graphical illustration of the patterns we're finding. And then asking them, can you prove what you're seeing? Can you prove the structure? And then for people who want applications, you can now start having them read up some stuff about chaos theory, with really small changes lead to very quick changes in behavior. One of the earliest uses of fractal geometry is in video games or movies and special effects. How many of you have seen the original Star Trek II Wrath of Khan, not the horrible remake? The Genesis torpedo, the Genesis planet. That was one of the first instances of using fractal geometry to render something in a movie. And so what I've done right now is I've got it going very slowly. So it's going up to the 178th, 180th row. Let's speed time up a little bit. And so let's go a little faster. So you can really start to see the patterns emerging. And again, if you were not lazy like I was, you could actually have it coming out as equilateral triangles rather than slightly forced. You just do it like this, it doesn't really make much of a difference. And so I think at this point it's about as fast as we can go. So this gives you an idea of what's happening. But now that we have this pattern, so some other things you could ask is, well, what other questions could you ask?
Patterns emerge amidst the numbers of triangles themselves.
Okay, say that again?
What patterns might emerge within the numbers of triangles themselves?
Okay.
I mean, I'm a big kind of pattern guy. I think that's what sixth grade teachers like to do.
Yep.
So I would be asking from relative.
How many triangles you have of this size? How many you have of this size?
Yeah, I was thinking of that.
Can you get a formula for something like that? Other questions?
How many triangles there are to row whatever.
Sure, how many triangles are up to a given row?
Yeah.
One more question, then I'll do two of the questions.
If you took the sums of the areas
Ah,
of one section, how are they related to the sum of the areas of that section plus the next section or something?
yeah.
No.
In the limit, what fraction of the, let's say we look at this, so this is going up to the 2000th row, but let's rescale so that this always goes up to 0, 1. So here, I will rescale, if I stop here and make this go up to 0, 1. I will rescale and make this go up to 0, 1. What fraction of that triangle is kept? What fraction is filled in? And you'll actually get an answer that's a non-integer. And so this is a nice introduction to chaos theory. What is the dimension of this set? I'll ask two more questions. I did something very simple. I did odd, even. Well, if I look at what happens if I divide by 3, I have 3 possibilities. I have a remainder of 0, a remainder of 1, and a remainder of 2. What would happen if I now colored things based on the remainder by a division of 3? So now all of a sudden I have a more colorful triangle. what would happen? And so that's another really good question to ask. And I want to end with a numerical question and then talk a little bit about a story proof, and then after that we'll take a brief break. Okay, so I think most people had seen this formula for n choose k. Is that correct? I think 2 or 3 people had not seen it. So I think for now I'm not going to go into why this formula is correct. I'm going to just say this is a formula for n choose k. And just have you trust me on that, and I'm happy to talk about it later. Have you seen factorials? So n factorial means multiply n by all the numbers down to 1. And so this is just a really good way of encoding n choose k. So what I want to do is I want to talk a little bit about how you would prove the formula for Pascal's triangle. We proved it by expanding things out over here. And in this proof, I never had to use n choose k. Right? This proof was perfect. It just said every coefficient comes from taking the 2 ones above it and adding them. Great, but if I don't know those 2 coefficients, I then have to go through the whole triangle if I want to compute something. So this n choose k is n factorial over k factorial n minus k factorial. That allows you to just jump to wherever you need. And so what I want to talk a little bit now is efficiency of computation. And this is something that's really not done nearly enough in my mind in the school systems. It's great to have a formula for something, but if the formula takes so long that it's not useful, then this isn't good. So a great question is, if you have students, especially students who like to compute a program, how would you write a program to construct Pascal's triangle, modulo 2, just using this even and odd thing? So it's a lot of very interesting technical issues as to how would you have it do this in real time. I just got a new computer and I just tested it out this morning, and it's still not fast enough to really compute this in real time. I cheated. I saved the results into a file, and I'm reading it into the file. But how would you compute things in a real short amount of time? And so I think that's a really good unit to do now. And so I'll go back to the Babylonians and show what the Babylonians did. I'll leave this for now. So, in terms of Babylonian mathematics, what are they most famous for? Nope. Degrees. So, what about degrees?
They thought there were 360 days in a year. So
Yes. So the Babylonians gave us base 60. Okay. Now, base 60 has a lot of very nice advantages. I know at least one person used to be administrator and has now come back to the good side. When you're forming committees, you like to have numbers that are very divisible. 12 is a great number. I would be very hesitant to be in an organization with 60 people dividing it up, but 60 splits many ways. 60 is a good number like that. Okay. Mathematically, the universe doesn't care that we like 60 and that we have 10 fingers. If the universe is going to care about anything, it'll either be 2 or more likely E. But the Babylonians gave us 60. Right? I will assume everybody knows the multiplication through the 10 by 10 tables. And 11 by 11 is not too much of a challenge. How about 12 by 12s? I'm not so good at my 12 by 12s. 13 by 13? Anybody good beyond 15 by 15? Okay. So none of us have really gone beyond 15 by 15, but we don't need to. Right? We only need to go up to 10 by 10 because we work base 10. Well, imagine you're an ancient Babylonian kid and you're learning multiplication. So you've got to learn your 60s by 60s. So if you wanted to do x times y, how many things do you have to learn? 3,600. 3,600 things to learn. Fortunately, you have a great insight, and you realize it's not as bad as 3,600. What do you know about multiplication? Yeah, multiplication is commutative. So x times y is the same as y times x. So really, only about 1,800. As x times y equals y times x. It's a little bit more because you have to do the diagonals. So really, there's 3,600 things, 60 of them are from the diagonal. Take half of that and add back the 60 from the diagonal. If you know your choices, this is the same as choosing two numbers from 60. Well, if I do two numbers from 60, that does not include taking the same number twice. So I would then have to add 60 plus 1. And so it's about 1,800 things. How did the Babylonians store information? They, were about their cell phones, which I think have more computer powers than the Voyager spacecraft. They chiseled, right? They had these tablets. So if you don't remember all of your 60 by 60s, well, no worries, you can just carry your tablets and just look it up. Their tablet is a little bit different than the tablets we have today. Okay? I think somebody has a tablet over there. Yes, yeah, amazing how much of the Babylonian civilization you could put in that one. How many tablets would you like to carry around with you? One, right? So rather than multiplying x times y is y times x, the Babylonians were very clever. They said x times y is the following. X plus y squared minus x squared minus y squared divided by 2. And so if you look at this, on the face of this, this looks like one of the worst things you could possibly do. I want to multiply two numbers, so instead of multiplying two numbers, I'm going to do 3 squarings, 2 subtractions, and a division. This was before Christmas, so there's no partridge here. So, why is this a good trade?
You don't need to know as many
Right, what do I only need to know?
squares.
I only need to know my squares. Subtraction is easy relative to multiplication. Division by 2 isn't bad. So this is a great trade-off. So this is the lookup table. And so a lot of modern engineering, cell phones in particular, they all revolve around the need for devices like this with limited power to do difficult computations. So you store a couple of key values and you interpolate. So we interpolate. And so by knowing the squares and being able to subtract and divide by 2, this allows us to calculate x times y very fast. And so again, when I talk to my students, I ask them, how many of you really enjoy watching streaming video when it stops and you have to wait for the connection to refresh and to continue? It's not as bad now, unfortunately, as a couple of years ago, so it's not as powerful of an example for students. But you don't like to have to wait for things. How do you manage things? And so the whole idea of efficiency is extremely important. And most of the time, we just talk to our students about solving problems. We don't talk to our students about solving the problems well. It's not enough to have an algorithm that will give me the solution. I want to find the solution in a reasonable amount of time. And so for the Babylonians, this is a faster way to calculate it than having to memorize all of those more complicated rules. And so to me, this is a springboard to something like that. So if I want to do Pascal's triangle, if I want to calculate these things modulo 2, the question is, how do I do it? How do I store? If you're really good at CS, you can write a much more efficient program than what I did. I wrote a very inefficient program, but still mildly more efficient than just pure brute force. So if I want to calculate Pascal model 2, the question is, what's the best way to do this? Well, one way is I could compute each coefficient. I could use my n choose k formula. And then I could look and see is it even or odd. But that's very expensive. So a much cheaper way of doing it is if I know the values of a given row, and I'll put it, I was using green for, I'll use black. So let's say I know certain values, value 1, value 2, value 3, value n. And I know this is going to be odd, this is going to be odd. If I have this row, I can calculate the next row by just parity. Right? And so I can use parity and I can figure out what this is. So all I need to do is know the value of a given row, and then I can get the next row. Okay? Well, what if I only want to investigate Pascal's triangle not from the very beginning, but from some point later down? I don't want to have to compute the whole triangle. I need one row for this parity trick to work. Well, I could always use this formula, but this formula is expensive. And so is there a way for me to compute one row without too much work? And so as an exercise, n choose k is n factorial over k factorial n minus k factorial. N choose k plus 1, the next term, is n factorial over k plus 1 factorial n minus k plus 1 factorial. I find it's always good to put in parentheses. One of the most common sources of error is not putting in parentheses and distributing incorrectly. So I want to do some pattern comparisons. How is this similar to this? Well, instead of having k, k minus 1, k minus 2, I have this extra factor of k plus 1. So let me pull out a k plus 1. I have an n factorial here, I have a k factorial here, but now I start at n minus k plus 1. This starts at n minus k. I want to put in an extra n minus k down below. So I'm now going to do my second favorite thing in mathematics. I'm going to multiply by 1. If I multiply by 1, I don't change things. So if I want another n minus k down below, I have to multiply by an n minus k up above. And I get n minus k factorial. So what this tells me is, if I know a binomial coefficient, I have a very simple formula to get the next coefficient. I don't have to compute from scratch. I just take my previous answer and I multiply by, so my previous answer, and then I multiply by n minus k over k plus 1. And so now if I want to jump into a calculation a little bit later, I can do this. And so one of the other topics that might be worth discussing today is the connection between Fibonacci numbers and gambling. So the Fibonacci numbers are actually related to playing roulette in Vegas. And so formulas for the Fibonacci numbers, being able to jump to a certain Fibonacci number is very useful. So this is another part of this problem that I really like, is this idea of talking about efficiency. And for the students who are looking at applications, if they have the ability to experiment, you can do this with an Excel spreadsheet and see how far down you can go. And then trying to do things quickly. And then tell them, well now, what if I want you to start at the 200th or the 300th? Can you just jump there, or do you have to calculate everything? How would you do these calculations? How would you try to do it in a reasonable amount of time? So the last thing I want to do, and then we'll end this unit and then we'll take a break, is to show you a proof of Pascal's formula, that you add the two by telling a story. And so this is probably going to be, this would definitely be too hard for, I think, middle school students in terms of what they've seen. But for those of you in high school, how many of you have worked with binomial coefficients in your classes? Okay. Have you done any combinatorics or probabilities? So hopefully this is something that you could then use. So I'm going to just do a small subset of Pascal's triangle. Let's say that this is n choose k over here, and this is n choose k plus 1 over here. This would be n plus 1. Okay. So I want to prove that this plus this equals this. Can somebody give me one way to try to prove this? I don't care how bad or painful the proof is. Can you give me some idea of how we could try to prove this?
Travel and car rentals.
Yes.
Use that formula.
We could use that formula. And so we could just go through and just do the algebra. N choose k plus n choose k plus 1 is n factorial over k factorial n minus k factorial plus n factorial over k plus 1 factorial n minus k plus 1 factorial, lots of algebra, and then C, it's n plus 1 factorial over k plus 1 factorial n minus k plus 1. So if your students are patient enough, they will get it. They will also hate you, they will hate mathematics, and they will be extremely unlikely to ever want to do any of this again. This is a valid proof. And for me, when I'm trying to prove something, I first want to know, do I have a method that will work? Can I hack away and get it? Good, I can. Now can I find a better way, a more enlightening way to get a sense of what's going on? At the end of the day, I have no idea why this is true. Right? This is just so, oh, an algebraic miracle occurs, and at the end of the day, it simplifies to this. Wonderful. So I want to give you a story proof. A couple of years ago, I was writing notes for my probability class, and I found that I was writing in Dr. Seussisms. It was very late at night, and I realized, okay, that was time to stop. But I do want to go back to Dr. Seuss today. How many of you have read the Starbelly Sneetches? Or I think it's just called the Sneetches. Okay, so there are two types of Sneetches on beaches. There's those with stars on their bellies, and those that don't have stars on their bellies. Okay? So, it's very tough for me being at Harvard not to break the board into Yale and Harvard with one really good, one really bad, but since this is being recorded, I will do the two types of Sneetches. So we will assume that there are n Starbellies. Well, there are n Sneetches without stars, and then one Sneetch with a star. Okay? And I want to form a group of k plus 1 Sneetches. I want to choose k plus 1 of the n plus 1 Sneetches. Okay? Well, by definition, that's just n plus 1, choose k plus 1. That's how we've defined the binomial coefficient. It's the number of ways to choose this many objects from that many objects. So now I'm going to tell you a story. Well, there are two possibilities when I'm forming my group. Either I have the one with a star, or I don't. If I have the one with the star, so case 1, have the star in group. Well, I need k plus 1 Sneetches total. I have one Sneetch. How many more Sneetches do I need? And how many Sneetches are available to be chosen? So how many ways can I do it? And choose k. Case 2. Don't have the star. So how many Sneetches do I need? And how many are available? N. So how many ways are there to do that? Other way around. And just k plus 1. So this sum must equal this. Those are the two different ways of forming a group of k plus 1 Sneetches from n Sneetches. And I break it up into, I have this extra special Sneetch, or I don't. Now, of course, this is contrary to what Dr. Seuss is trying to teach us in the book, that there is no difference between the Sneetches with stars on their bellies and not. But I will leave the literary implications for the moment. Okay? It's very useful to consider the Starbelly Sneetches as special. What's really going on here is I'm telling a story. There's lots of different stories you can tell in probability and combinatorics. One of the most important stories is that n choose k is the same as n choose n minus k. And again, you could prove this by doing algebra, or you could do it by telling the story. I have n people, and k people are going to be hit with a committee assignment. How many ways can I choose those k people? And choose k. Another way of looking at it is, I have n people, n minus k of them will not be hit with a committee assignment. How many ways can I choose the n minus k people not to be hit? And choose n minus k. So a lot of these combinatorics problems can be reduced to telling stories. And this is sometimes a hard thing for students to learn. It's a hard thing for researchers in the field to learn. How do you tell the same, how do you express the same event two different ways? How do you look at something in two different ways? Well, one way is easy, sometimes in one way is hard. And if we can then somehow relate the two of them together, we can make great progress. So for me, there's a lot of great stuff in Pascal's triangle. There's a lot of wonderful things it leads to. The real question is, how much time do you have? Can you color units from something like this? We got to see interesting patterns emerge. So you have geometry. You can also have the students try to create their own problems. And again, I think trying to get students to ask questions earlier rather than later is a great thing to do. Another thing you can do is talk about efficiency of computation. How would you actually compute these things? These computers, these phones we have in the background, they're doing all this work for us. How are they actually doing the work? And so talk about the Babylonian mathematics, about how the Babylonians would do something like that. To me, it's very interesting. And if you teach, how many of you have taught linear algebra, matrices? So if you do matrices, there's something called the Strassen algorithm to multiply matrices faster than you would expect possible. And you wouldn't believe how many applications this has. So it's all about efficiency. It's all about doing things faster than you're used to being able to do them. And so that could be another thing we'll talk about. But I think at this point it's worthwhile just have a few minutes of break. Just stretch your legs,